Hey, so we all use the internet every single day, right? But have you ever really stopped to think about how it actually works? It feels like pure magic. You click a button and poof, something from the other side of the world appears on your screen. But behind that curtain, there's this incredible system of actual physical wires, invisible rules, and just some brilliant, brilliant engineering. Today, we're going to pull back that curtain.
Just think about it for a second. You hit send on an email, you post a photo, you click on a link. In literally the blink of an eye, your data is zipping across town, maybe even across the entire planet. What on earth is happening in that split second? Well, that's the journey we're about to go on. And we're starting with the most basic question of all. What even is the internet? All right, first things first, let's just get one thing straight. The internet is not some fluffy magical cloud floating up in the sky. Nope. It's a very real, very physical thing. At its absolute core, it's just a gigantic network of networks, and it's really made up of three basic physical parts.
Okay, so part one is something called a host, or what the engineers would call an end system. This is basically any device that's connected to the internet and running an application. So yeah, we're talking about your laptop and your smartphone, for sure. But it's also those massive servers in data centers, your smart TV, heck, even a smart toaster that can tell you the weather. If it's online, it's a host. So all these hosts have to be connected somehow, right? That's where communication links come in. These are literally the physical roads of the internet. They can be fiber optic cables buried deep under the ocean, the old copper telephone wires running into your house, or even invisible radio signals like Wi-Fi and 5G. And that term you always hear, bandwidth, that's just how much data these roads can carry at once. And finally, the third piece of the puzzle, packet switches. You should think of these as the traffic cops of the internet. See, when you send data, it doesn't go in one big piece. It's broken up into little chunks called packets. Devices called routers and switches look at each packet and direct it along the best path to get it where it needs to go. So you've got billions of devices, all connected by millions of miles of cables. How do they all communicate without it just being total, absolute chaos? Well, it turns out they all agree to follow a very strict set of rules. And in the networking world, these rules are called protocols. You know, the easiest way to wrap your head around network protocols is to think about our own human protocols. We use them all the time without even noticing. If you want to know the time, you ask a specific question, right? Got the time? And you expect a specific kind of answer. Network protocols, like the famous ones TCP and IP, they do the exact same thing, but for machines. They define the format, the order of the messages, and exactly what to do when a message comes in. So when your computer wants to get a web page, it follows a very similar pattern. One machine sends out a request. It's basically saying hi. The other machine sends a response, hi back. Then the first one asks for what it wants. Can I have this file? And the second one sends it. It's this simple, structured back and forth conversation that makes the entire system work so smoothly. Okay, so we've got the components and we've got the rules, but how do you and I actually get on the internet from our couch? Well, that happens through something called the access network. Think of it as the critical on-ramp that connects your personal devices to that global internet superhighway. Now, for most of us at home, this on-ramp comes in one of two main flavors. You've got DSL, which uses your existing phone line. It gives you a dedicated connection, but it's usually a bit slower. Then you have cable, which uses the TV network. It's generally faster, but, and this is a big but, it's a shared resource. That means your internet speed can sometimes slow down if all your neighbors decide to stream movies at the exact same time. All right, that gets us from our couch to the on-ramp. Now, let's merge into traffic and dive into the internet's core. Once your data is on that highway, it travels through this massive, tangled mesh of routers. And the way it travels is all thanks to a truly revolutionary idea called packet switching. To really get why packet switching is so awesome, you first have to understand the old way of doing things, circuit switching. This is how the old telephone networks worked. When you made a call, the network reserved a dedicated private line just for you and the other person. But here's the catch. If neither of you were talking, that entire connection, that whole resource, was just sitting there completely wasted. The internet totally flipped this idea on its head with packet switching. Instead of reserving a whole line, your message gets chopped up into those tiny packets we talked about. Each packet then finds its own way through the network, and the resources are only used for the instant a packet is actually being sent. This means the network can be shared way, way more efficiently by tons more people all at once. And I mean, the difference in efficiency is just staggering. On a single network link, A circuit switch system might only be able to handle, say, 10 users. But with packet switching, that very same link can support more than 3 times as many people. This isn't just a small tweak. This efficiency is the fundamental reason the internet was able to grow from a tiny research project into a global system connecting billions. So if it's so efficient, why do we still get that dreaded lag? Well, it's because every single one of those little packets has to clear 4 potential speed bumps. First, the router has to process it, check for errors. Then it might have to wait in a queue, basically a line, behind other packets. After that, it takes time to actually transmit all of its data onto the wire. And finally, there's propagation delay, the literal time it takes to travel the physical distance. Now, when too many packets show up at a router at once, those queues get really long. And if they get too full, the router just starts dropping packets. And that is the frustrating source of lag and lost data. We've been talking a lot about links and connections, but what are they actually made of? What is the real physical stuff that's carrying all of our ones and zeros across the globe? It really all boils down to 2 main categories. You've got guided media, where the signal travels through something solid. Think of the copper wires in your walls, that thick coaxial TV cable, or amazing fiber optic cables that send data as pulses of light. And then you have unguided media, which is just a fancy way of saying wireless. Radio waves carrying your Wi-Fi, your cell signal, and satellite data right through the air. Okay, we've got hosts, links, switches, protocols. This whole thing is an incredibly complex system. So how on earth do you manage it all? The answer is what I like to call the internet's secret sauce: layering. Probably the best way to understand layering is to think about air travel. A whole trip is a super complex process, right? But we break it down into manageable layers. You've got a ticketing layer, a baggage layer, a boarding layer, a routing layer with air traffic control, and so on. Now here's the genius part. The person checking your ticket doesn't need to know a single thing about how the pilot flies the plane. Each layer just does its own job and trusts that the other layers are doing theirs. The internet is organized in the exact same way, using what's called a 5-layer stack. Right at the top, the application layer worries about your web browser. Below that, the transport layer makes sure your data gets there in one piece. The network layer is the one that figures out the route across the whole internet. Then the link layer handles the connection to the very next device in the chain. And finally, the physical layer just worries about turning data into electrical signals or flashes of light. This modular design is what makes the internet so incredibly powerful and easy to update. So there you have it. From hosts and links to packets and protocols, that's the fundamental architecture of the internet. And what's wild is that it's a design that has worked amazingly well for over half a century, which, of course, leaves us with the big question. As we connect trillions more devices and demand speeds we can barely imagine today, what will the internet of tomorrow need to become?